Okay, so we are very happy to have Professor Frank Nijhoff from Leeds University. He'll talk about what's that? Lagrangian multiforms, the Darboux-KP systems, and the Chern-Simons theory in infinite dimensional space. So please start.
Okay, thank you very much, Professor Hamanaka, for the invitation to give a talk at Nagoya University. This is a new experience for me. I want to talk about some development in Lagrangian theory of integrable systems, which we call Lagrangian multiform theory. And that has been developed since 2009. And I want to focus in particular on a kind of three-dimensional example here, which is in some sense a kind of master example for integrable systems, as I will make clear. And that's the thing that I would call the Darboux-KP system. I don't have a good pointer, but can you see the cursor on the screen?
Yes, I can see. Yeah.
Okay. So I'll use the cursor for point as a pointer. And then very recently, we actually understood a very intriguing connection with Chern-Simons theory. And that is work that is in progress with two colleagues at Leeds, Dr. João Faria Martins, who is at Leeds, and a PhD student, Daniel Ricumbeni. So I want to explain that, and that connection with Chern-Simons theory may open some new kind of perspectives, not only on integrability, but maybe even on Chern-Simons theory and other fundamental areas of physics. Okay, so I will try to give here a brief outline of my talk. So I will start with a very brief introduction of Lagrangian multiform theory, which explains the basic idea and also gives a kind of key example, which I think explains a lot of the things that are going on in this Lagrange multiform theory. So this is an example of a Lagrangian two-form, and that describes systems of two-dimensional equations in 1 + 1 dimensions. But then I want to move to 3 dimensions, and that's where I will present then what I call the Darboux-KP system. And this is a kind of universal system that generates, in some sense, the entire KP hierarchy. And what I want to establish there is the Lagrange three-form structure, so it fits into the scheme of Lagrangian multiform theory. And then that's really the new result, is the interpretation of this theory as a kind of very strange and curious Chern-Simons theory in infinite dimensional space. And that may then maybe make connections with other areas of physics, actually. And in particular, I want to make a comparison with going back to 2 dimensions, so 1 + 1 dimensional field theories, where there have also been some interest in setting up action functionals of the Chern-Simons type. So we'll make a little bit of a comparison between what we are doing and what has been done in the literature. So I will not in my talk go very much into discrete integrable systems, which actually has been in some sense the motivator for the setting up the theory. But I will have to occasionally refer to some discrete systems in the background, because they actually form part of the structure that explains what is going on in this Darboux-KP system. So that is a bit of the outline of the talk. I've given recently a talk in the ECM conference that was more towards the discrete and semi-discrete parts of the theory, but I don't have the time to touch on that in detail here. Okay, so what is, or rather, why do we have a thing that's called Lagrangian multiform theory? So one of the things, I was always interested in Lagrangians from my students days actually, where I have a little bit of a background in field theory, whereas in integrable systems it has been much more conventional and common to talk about Hamiltonian structures in the context of integrability. That of course comes from the fact that integrability is often understood in the sense of Liouville integrability, which means that there is a kind of Hamiltonian theory behind that. But I was always interested in the Lagrange aspect. So one of the questions that I posed actually since a long time is how to capture the property of multidimensional consistency. So this, I will tell you what I mean by that. Multidimensional consistency is a term that I will use quite often, so I will abbreviate it by MDC. And that is for me a kind of key integrability feature. So, and the question is how to capture that multidimensional consistency in a Lagrange formalism. Okay, so what is that multidimensional consistency? What do I mean by that? Well, that is a very well-known phenomenon, if you think of it, is that actually many integrable equations, well-known integrable equations like the Korteweg-de Vries equation and also the Karamzev-Petriashvili equation and many others, they don't come on their own as isolated equations, but they actually come in whole, actually infinite families often of equations, which are all compatible with each other. So, and that is manifested in various ways. So for instance, in continuous integrable systems, you can think of commuting flows, the existence of higher symmetries, actually infinite number of conservation laws is part of that as well, the existence of so-called master symmetries, and so on and so forth. So actually, in fact, the existence of an underlying infinite dimensional Lie group or Lie algebra that is responsible for this multidimensional consistency. And in the discrete case, it manifests itself as well, namely through a property that we call consistency around the cube, which is a consistency when you have a two-dimensional discrete equation and you embed it in higher dimensions, and then there is a kind of move in 3 dimensions that needs to be consistent and compatible, and that is consistency around the cube. I will not go into details, but also the existence of Backlund transforms, which are discrete transformations and which allow for the kind of compatible structure. And as well, also in discrete systems, you have higher continuous symmetries and commuting discrete flows and so on and so forth. So all these things, all these phenomena are part of what we call multidimensional consistency. And so we can think of this in the following way. Suppose that you have a dependent variable in your system, let's call it u. So this is a function of actually if you solve an equation, it may be a function of 2 variables, but actually it is then, if you have a hierarchy of equations, it can be a function of many variables. So there can be many discrete variables. So these are indicated by this n1 and 2. So these are meant to be discrete variables in the sense that they shift by units. Or you have continuous variables like the space variable and higher time variables. And so if you have a multidimensional consistent system, then you have a solution which can be simultaneously a solution of a whole, maybe an infinite sequence of equations. And this function then depends on all those variables that appear in that hierarchy. And they are compatible. So you can have the one and the same function that obeys all those equations at the same time. They're not in conflict with each other. So that is the notion of multidimensional consistency. And that is, in some sense, the key integrability feature of many of the equations that we now consider to be integrable. For instance, equations that possess soliton solutions and whole classes of infinite classes of solutions, they will generally have this property of multidimensional consistency. So the notion of compatibility is very important here. So then, coming back to Lagrangian theory, there is a problem there, because the key problem is that when you have a variational approach, suppose that you have you have your preferred integral equation, like for instance the Korteweg-de Vries equation, then you can often write down without much problem, you can write down a Lagrangian for it. But that's where it stops. You have then one Lagrangian. And then if you then ask the question, well, what about the higher order KdV equation? That maybe has also a Lagrangian, but these Lagrangians are kind of separated. They have nothing to do with each other as they appear. You can write down Lagrangians for every equation in a hierarchy, but what is it that connects these Lagrangians together? And in the context of discrete systems, we kind of found an answer, and that is what we call a Lagrange multiform. And that is actually that, in fact, these Lagrangians are just components of a higher object, namely a differential or difference form in higher dimensions. And so that idea was put forward. In hindsight, it's a very obvious idea, of course, but nobody so far had been able to really give it any kind of credence. And we proposed that in this old paper in 2009, which kind of started the subject. And the important finding in that paper was actually a property of these Lagrangians that we call the closure property. So that closure property that we discovered in that paper in the context of discrete systems was really the key trigger that actually triggered the onset of this idea. So let me explain it in an example how this works. So this is an example, very simple example of a continuous Lagrange 2 form. And this example is actually due to Urysourys. And suppose that we look at the following situation. Suppose that we have a dependent variable which depends in principle on 3 variables, x1, x2, x3. And the derivatives are indicated by an index. So u1 means du, dx1, etc. And double indices indicate higher partial derivatives. Then we can write down the following Lagrange functions. And so far, these Lagrange functions are just what they are. They are nothing. They are Lagranges for an equation. So if we look at this L12 here, where we have derivatives with respect to x1 and x2, this in fact is a Lagrangian for the sine-Gordon equation. So you can see that here, if you write down the Euler-Lagrange equations, you get the sine-Gordon equation. So this Lagrangian is supposed in an action functional to be integrated over x1 and x2 in a space of x1, x2 variables. So over a 2-dimensional integral. Then we have this Lagrangian L13, and that's a separate thing. And this is supposed to be integrated over x1 and x3. And even though I used here the same symbol, u, so far these Lagrangians have nothing to do with each other. So if we write down the Euler-Lagrange equations, the conventional one, what we get is an equation of this type, which in fact actually is the modified KdV equation. So we have one Lagrangian, the L12, which gives the sine-Gordon, the L13, which gives the modified KdV equation. And so far, they're totally separate. But it so happens that the sine-Gordon equation and the modified KdV equation are connected by the fact that they're actually in the same hierarchy of equations. In some sense, the sine-Gordon can be considered as a negative flow to the modified KdV equation. And that is significant. So then there is this L23, which actually is supposed to be integrated in an action over the variables x2 and x3. Now this L23 is a bit funny because actually there are also derivatives here with respect to x1, which are not supposed to be there. And so we call them alien derivatives because this L23 has to be integrated over x2 and x3. And if you write down Euler-Lagrange equations for these L23, then actually these variables cannot be these derivatives cannot be get rid of by the well-known integration by parts trick, because the integral is over x2 and x3 and not over x1. So if we look at the Euler-Lagrange equations for with respect to u, we have to consider this u1 and u11 as independent, separate independent dependent variables. So we get this Euler-Lagrange equations for from the conventional approach to varying with respect to u, and that gives us some relation here of this form, which in fact actually is a kind of consistency relation. We call it a corner equation. But then we have also these additional derivatives where we consider u1 and u11 as independent variational variables, and they give us rise to separate constraints. But actually this constraint is nothing else but the derivative of the Sine-Gordon, and this is the Sine-Gordon itself. So actually the Sine-Gordon is sitting inside these two alien derivative equations. And it turns out that all these equations, so all these three Euler-Lagrange equations, are compatible with each other. In fact, this U23 equation is compatible. So you can check that by taking, for instance, the U1 derivative of the X1 derivative of this equation, and then compare it with the, for instance, the X2 derivative of this equation, and then everything fits. So this suggests that all these three Lagrangians, even though they are initially separate and they sit in separate spaces in your in terms of the independent variables, they form a two form. So here's this two form L, which has now components with these three Lagrangians. And when I interchange the indices here, I pick up a minus sign. That's by convention that we want the form to be antisymmetric. Okay, so so I could have written this Lagrange two form in various ways. I could have multiplied any of these Lagrangians with a factor and an arbitrary factor, and why not? So why do I choose this particular combination? So I've chosen these Lagrangians in a very particular way. Well, that is because there is now a very remarkable property that happens for this two form, and that's the following. If I take the derivative, the derivative operator on this two form L, so I get a three form. So you just compute this combination on the components, which forms the coefficient of this x1 wedge x2 x3, then it turns out that this factorizes. And this is typical for what happens in these multidimensional consistent systems if you choose the Lagrangians in the precise way that you do. So you have to adjust the coefficients in a very particular way. And then there is a way where this DL actually factorizes, and it factorizes in two forms. If you look at these factors, then this is just the form of the Sine-Gordon equation, and this is actually the form of the potential modified KdV equation. So actually, so that is what we call that this derivative of the two form has a double zero, and the double zero is factorized in parts of the equations of motion that we are after. So on the equations of motion, so either on the Sine-Gordon or the modified KdV, this form is actually closed. So I wrote here on Euler-Lagrange equation, so DL is closed, but using the equations of motion. And that is what we call the closure property or the closure relation. And this is very significant because what that means is that when you now write down an action functional, so this is then the integral of in three-dimensional or higher dimensional space of this two form L over some arbitrarily chosen two-dimensional hypersurface, then on the equations of motion, so on the solutions of the Euler-Lagrange equation, so when you have solutions of Sine-Gordon or modified KdV, then this action functional is actually independent of the surface. So you can deform the surface in any way you want in this three-dimensional or higher dimensional space, and the value of your action functional remains the same. And that is the key that is one of the key aspects of this multiform theory. So if we take variations, okay, let me be more precise. So how do we then formulate this multiform principle? Well, the action functional is now not only to be considered as a functional of the field variables, the u's, as in conventional variational theory, but it's also functional in some sense of the surface over which you integrate. So the dependent variables, which are the field variables, and the independent variables, the sigmas, they play a kind of, they are now kind of on the same footing in this theory, and that you want the action to be critical with respect to both the variations in the dependent variables, as well as with respect to variations, so deformations of the surface over which you integrate. So there are two kinds of variations that we consider, either the very infinitesimal variations of the fields, well, actually at the same time, variations of the field as in conventional theory, but at the same time also variations of the surface. And these variations with respect to the surface, they give rise to this closure property. So the closure, it's basically saying that if you deform the surface, then your action has to be critical, and that means independent of the deformation or invariant under deformations of the surface. And that is now the remarkable structure that's going on, because we have two types of variations that kind of play together in order to create this structure. But at the same time, that makes it also possible to derive not only one equation from the Lagrangian, as in conventional theory, but actually a whole hierarchy or a multitude of equations at the same time. So the derivation, so you have an extended set of Euler-Lagrange equations. It's no longer just the usual Euler-Lagrange equations that arise from this theory, but you have an extended set of Euler-Lagrange equations. And that is quite complicated, because you see it will also contain, for instance, these extra constraints that come from these alien derivatives, and they come from what we call corner equations and so on in the Euler-Lagrange setup. So the whole structure of the Euler-Lagrange equations that are associated with this theory is more complicated, but it can be seen in a very simple way, namely in the following way. If you think of a surface which is a closed surface, so take for our sigma, so we can choose any sigma over, and we demand that the Euler-Lagrange equations are valid for any sigma at the same time. So we can take for the sigma, we can take the closed surface, which is the boundary of some ball in our d plus one-dimensional space. And then by Stokes' theorem, that is equal to the integral over the ball itself of the derivative. So when we do variations of the action, it is essentially moving the variation through the integral. It is basically the variations of this derivative of L that plays a role there. And so the Euler-Lagrange equations can be kind of somehow captured all together in a very concise form by saying that delta dl is 0. So if we look at this example here and we do the delta of this action, then actually we get, of course, because of this factorized form, this double zero form, we get a delta, for instance, of this factor, but then that vanishes because this equation is satisfied, or we get a variation of this factor, and then that vanishes because then the DL vanishes because this the Sine-Gordon is satisfied. So in this way, you derive from the Euler-Lagrange equations not only one equation, but actually a multitude of equations, and that is precisely what we wanted to achieve, namely that a variational principle from which you can derive not one single equation, but actually an entire multidimensionally consistent system of equations. Okay, so that theory, this is a very simple example, but it highlights the key points. And this theory has been developed now since we started with it in various directions. We have seen that many integrable equations and integrable hierarchies actually fit into this variational scheme. And let me just point out a few main differences with conventional variational approach. So I'll call it LMFT, Lagrange multiform theory. So what are the essential differences with conventional least action principle approach to which we are used to and we learn about as physicists from our early stages? Well, first of all, that the Lagrangians are no longer just functions, or you could say volume forms, but they are actually genuine differential forms with non-trivial codimension in a space of independent variables which could be arbitrarily large, an arbitrary, perhaps infinite space of independent variables. So we have genuine forms, not just volume forms. And furthermore, that, as I already indicated, that the action functional is not only a functional of the field variables, but also of the independent variables in the sense of the surfaces over which you integrate. And so we have variations not only of the fields, but also of the surfaces over which we integrate, the hypersurfaces in the multidimensional theory. And in that way, as I indicated, it produces a multidimensional system of equations rather than just a one single equation, which you would normally get if you have just a scalar field Lagrangian. And then you have this generalized Euler-Lagrange equation system, which I don't want to show because it's quite a complicated set of equations. But the most dramatic difference actually is the last point, actually, that since these Lagrangians have to be very special because they represent an integrable theory, they actually can be considered no longer just to be the input that you do when you set up a theory in the usual conventional theory, but they are actually solutions of the principle itself, in the following sense. If you take any theory in physics that starts from a variational principle so far, then usually the Lagrangian itself comes from outside. It comes from, it's being put in by hand, or it is kind of somehow constructed from secondary or tertiary considerations like symmetries, gauge symmetries, and so on. But it doesn't follow from the principle itself, what the Lagrangian is. You have a choice there. In this theory, when you write down the whole set of Euler-Lagrange equations, then the Lagrangians can be considered to be solutions of this whole set of equations. So it is no longer the case that the Lagrangians are the input, but they are themselves solutions of this system. And that, of course, could be considered as very restrictive. And of course it is, because we set up a theory for integrable equations. But on the other hand, from a point of view of foundational physics, this would be very desirable because it removes a lot of arbitrariness when you set up a fundamental theory. In fact, the principle itself, the multiform principle itself, should tell you what the Lagrangians are. And in fact, part of that, now the Euler-Lagrange system is a very complicated system of, in fact, PDEs, and it's very difficult to solve that in general. But under certain restrictive assumptions, we have already done that and actually derived the Lagrangians from the Euler-Lagrangians, from the whole set of Euler-Lagrange equations. And then there are certain parameter freedoms that you still have, and those freedoms are corresponding to integrable systems. So, as I said, this whole idea of multiforms was initiated in this paper in 2009, and then there was a lot of work done also at the Technische Universität in Berlin by notably Alexander Bobenko and Yuri Souris, and there are many collaborators. And so the theory has been moving forward quite a bit in the past decade or so. The main aim for me actually for the future is actually the quantum theory. So what is the corresponding quantum theory? And we made some kind of initial steps towards a quantum theory in this paper with Stephen King. So for very simple examples, namely quadratic Lagrangians, but we have established already a kind of analogous property to this closure property for the case of Feynman propagators. So this is in the context of Feynman path integrals. Okay, so maybe I should ask if there are any questions at this stage. If
Yes,
not,
I have one question.
Mm-hmm.
So your Lagrangian would have some symmetries, and data charge would be calculated, I think. And on the other hand, integral systems have infinite conserved quantity. So is there a relationship between them?
Yes, there is actually. So I've given here a very simple example of where I've indicated two flows, but actually, in fact, one can consider the Sine-Gordon to be a symmetry of the modified KdV and vice versa. So in some sense, these equations are already the symmetries of each other in some sense. And you can extend this whole hierarchy to an infinite hierarchy and then fit all the corresponding Lagrangians into that. And then you get a multiform structure with an infinite number of terms here. And they would fit in that way. But then, of course, you have also to add additional independent variables. So instead of having just x1, x2, x3, you would have an infinite sequence of higher independent variables, x1, x2, x3, x4, etc. And they all form symmetries of each other. So in some sense, Noether's theorem, which kind of makes the connection between symmetries and conservation laws, is somehow incorporated in the structure itself, because the equations are each other's symmetries somehow. And so the fact that we have this double zero construction was actually motivated by the idea of symmetries and conservation law, because this is actually conservation law itself, actually, this closure property. And one can consider to be these factors. Suppose that we consider this to be the Euler-Lagrange equation, then this would be considered to be a characteristic of the symmetry. And vice versa, if Sine-Gordon is our main equation, then this would be the characteristic for the symmetry that is associated with the modified KdV equation. So symmetry it's very kind of incorporated somehow into the theories. Does that answer the question?
Yeah, that's a very good story. So it's already discussed in some paper.
Yeah. There are some papers. There was a paper by Souris, Petrera, and Vermeeren, and we have a paper also with Vincent. I refer to it later on.
Lagrangian or something.
Yeah.
Okay. Yeah. I'll check. Thank you very much.
Okay, you're welcome. Okay, so I want now to move on to the three-dimensional case, and this is, we somehow know in integral systems that the Kp equation, so the Kadomtsev-Petriashvili equation, which for those who are not familiar with this theory, is a two-dimensional in space generalization of the KdV equation. But if you take into account time, then it would become a 2 + 1 or three-dimensional equation. And this Kadomtsev-Petriashvili equation has a hierarchy, which I don't want to develop here. But when you write down the conventional hierarchy of the Kadomtsev-Petriashvili equation, we found a Lagrange multiform structure for that, but it is very convoluted in the sense that it relies on the representation in terms of pseudo-differential operators, which is not, from my perspective, the most convenient one. So what I wanted to present here is actually what I call the Darboux-KP system. And that is the realization that actually when you do a trick, the trick is you sum the whole hierarchy together in terms of some new variables, and these variables are called the MIWA variables. And I will come with some explicit formulas later, but in terms of MIWA variables, then the equations look much simpler and much more concise. And so when you do that for the Kadom-Sepet-Villachvili hierarchy, you get this system here. That is what I call the Darboux-KP system, or generalized Darboux system. Now, this is very, it was already known by people like Martinez Alonso and Konopachenko that the Darboux equations have a connection in terms of have a connection to the KP hierarchy in terms of MIWA variables. And so the MIWA variables here are these psi p's, and they carry an index, a label, which is P, Q, and R. And I call them P, Q, and R because actually these P, Q, and R are not necessarily integers. They are, in some sense, they are continuous variables, continuous parameters, which play a dual role in the theory, namely as lattice parameters for an underlying discrete system. I will come to that a little bit in a few moments. But in this generalized Darboux system, P, Q, and R can take any kind of continuous values as well, and not only integers. So the original Darboux system, which were equations of the same type, were set up or constructed by Darboux and others. Lamé was also involved in the 19th century, and here there's a reference to study so-called conjugate nets for orthogonal curvilinear coordinates. And in the development of that theory, they come up with this number of equations which look exactly like the equations that I've written down, but then with integers, and then the integers range from, say, ij from 1 to n, and n is the dimension of your space. But here, actually, the equations look exactly the same as the Darboux equations of that curvilinear orthogonal conjugate nets theory, but they have a totally different interpretation. So these, where Darboux called them betas, I call them B. And as I already said, the indices here are continuous variables and play the role of some associated lattice parameters. Now, it was already realized that in some sense, this set of equations, and then you can extend that, is equivalent to the KP hierarchy. And I will make that hopefully a little bit more precise later on. But let's look at this system in its own right. So if we have a closed form system with 3 independent variables, xp, xq, xr, and a number of 6 actually field variables, and so we have 6 equations, and that forms a closed form system of equations. Now, the equations for the conjugate nets and the Darboux systems were studied from the point of view of integrability in the late 1980s and 1990s intensively, and were studied by using the methods of integrable systems, so-called delta bar systems and non-local Riemann-Hilbert problems, and so on and so forth. In fact, one of the persons who brought the system to the attention of the modern era was Volodya Sakharov, who sadly passed away about 2 weeks ago. They were heavily studied, and the integrability is well known for the equations themselves. What was not established was a kind of Lagrange structure for them, and that's what I did. Well, I'll come to that in a moment. But let me first make the point that this system itself, so this is what's called system 7, they form a multidimensional consistent system in the sense that we can embed it in a higher dimensional space. So these 6 equations live in a 3-dimensional space of xi-p, xi-q, and xi-r, but we can extend that space with additional variables and write down similar equations to the ones that are written here. And so, for instance, we can extend, for instance, with an additional variable xi-s with a 4th parameter, and then we have to introduce also the additional fields in this system and write down the corresponding equations. But the main point being that when you do that, then that whole system that is now in 4-dimensional or higher dimensional space is multidimensionally consistent. And that can be easily checked by cross-differentiation. So if you look at this cross-differentiation, so you take the ddxip of this quantity and then the ddqs. Now, of course, this has to obey the Darboux system and this as well. Then, of course, this is a requirement that you want for the quantities B to be proper functions of all these independent variables, xip and xis. But if you start from the equations that we had before, then it's not clear that if we take the xis derivative of this equation here, and we then compare it with the other way of doing the derivatives, that gives the same answer. But actually it does, and it is easy to do the computation and check that this actually holds using the equations. So this indicates that this is a multidimensional consistent system. And so then comes up the question, naturally, if there is a Lagrange multiform structure. And that requires first that we have to find a Lagrangian for that system. So that I did in that paper of last year. And here is the Lagrangian for the Darboux-KP system. So this is, in fact, for the moment, a kind of single Lagrangian for the 3-dimensional system that I've written down. So if you write down the Euler-Lagrange, conventional Euler-Lagrange equations from this Lagrangian, you will get the equations for the Darboux system. But I've indicated here already the indices that actually when we want to embed it in a multidimensional space, then we expect there to be a form structure. So a 3-form in this case, not a 2-form that we've seen in the earlier example, but a 3-form. And that has to do with the fact that we're dealing with 3-dimensional equations, but embedded in a multidimensional space of arbitrary dimensions. So if we stick to a 4-dimensional embedding space, then the 3-form takes this form, so with PQR, QRS, etc. So we have 4 variables. And of course, I can extend it to any number of variables, but let's stick to the simplest extension. And then what we want to do is to establish the double zero property. So we have to compute the derivative of this Lagrangian, and that's a direct computation. Just take the derivative of this with these coefficients. And if you do that, so it's a direct computation. So we compute this coefficients of the corresponding 4-form. So this is the DL is a 4-form. Then these coefficients A that appear there, they need to be computed, and they're given by this combination here. And then it turns out that this indeed has a double zero. Now, double zero means that it is actually a sum of factors, each of which is of the Darboux form. So each of these gamma represents a Darboux equation in the system. And clearly, when all the Darboux equations are satisfied, then this whole coefficient vanishes. And in other words, then this form vanishes as well. So, so this establishes, so this is a direct computation that you can do. And the only work that needs to be done is to somehow reorganize the whole expression in terms of these combinations of gammas, which is non-trivial actually that happens. And then you can conclude that if you look at the delta DL, that means the delta of this coefficient, then this vanishes whenever one of these gammas is 0, or whenever all these gammas are 0. So then the closure property is satisfied. And again, that means in this situation that when we look at a closed 3-dimensional hypersurface V in 4-dimensional space, So this DL lives in 4-dimensional space. Then by Stokes' theorem, you get integrated over the enclosed volume in four-dimensional volume. And then we have a similar argument as we had before, that if you take the variations of this S, then it amounts to the variations of this DL. And then if they vanish on the Euler-Lagrange equations, then the action is critical. So this establishes the three-form structure for the Darboux system. Now, there are a number of properties of the other properties of the Darboux system, which I want to skip over very quickly. First of all, for those who are familiar with integrable systems, there's also a Lux representation, so a linear representation, which gives you the equations of motion. And the funny thing is that from the Darboux system, actually, you can derive the Lux representation from the system itself. And that, again, relies on the multidimensional consistency. So, for instance, if we would extend the system in an extra dimension which contains a variable k here, or a variable L, so a parameter k, so where we had BPQ, we now have a BPK, and we can think of k as being the spectral parameter, and here a kind of associated spectral parameter, then this will give us a kind of function phi, where we suppress the k dependence, and the k is like a spectral parameter. And so the spectral parameter is sitting in this parameter space that labels the variables. And here's an adjoint variable, and they then obey these linear equations. So in fact, this is a whole set of linear equations, which forms the Lux representation or linear representation for this Darboux system. And here's a kind of adjoint version of it. You can then, you can notice that this is kind of inhomogeneous, because here we have a phi q and a phi p. They're different, so this is not really a homogeneous linear representation, the same here. But you can derive a linear representation by taking a further derivative, and then you get a kind of really homogeneous linear system. And that linear system is also sometimes referred to as the Lamé system. And the remarkable thing is actually that also the Lux pairs, or the Lux representation, sits in a multiform structure. So we can actually now, in some sense, copy over the Lagrange components from the original Lagrange structure here, and then write down a Lagrangian in terms of the psi's and phi's, and this then forms a Lagrangian structure for the Lux equation. And that is also a kind of new aspect, that actually the Lux representation itself has a Lagrangian or variational representation. So that's one thing. And another thing, and here I have to go a little bit into the discrete area, there is also a discrete analog of this Darboux system, which was studied in the 1990s and was first, I think, proposed by Bogdanov and Konopachenko, and independently and more or less at around the same time by D'Oliva and Santini. And so here we have a set of difference equations rather than differential equations, and they mimic in some sense the Darboux system. So if you compare it with the original Darboux system, a few pages back here, this system here is kind of reflected in the discrete setting by this system, where now the delta is a difference operator, and the difference operator is here a shift operator. So this TP means a shift in a variable n, a discrete variable that is associated with the parameter p. So the same parameter that we use in the Darboux system labels not only the MIMA variables, the psi p's, but it also labels some discrete variables in which you can do a shift, elementary shift. And then this is the difference operator, the shift minus the identity. And the only thing that really distinguishes the discrete from the continuous is that, in fact, you cannot really write it only in terms of the difference operator. You also need the shift operator still there. So actually, it's just a little bit rhetorical to write this difference operator here, because in fact, the shift operator is the more important quantity or operation in this discrete setting. And that has to do with the fact that in discrete systems, you don't have a really proper analog of the Leibniz rule for differentiation. The Leibniz rule, or the analog of the Leibniz rule for taking differences, also involves an extra shift that you can't get rid of. And that is a kind of somehow a complicated aspect of the discrete systems. But nonetheless, this whole system is, again, is integrable and is multidimensional consistent in a similar way as I explained for the original Darboux system. And not only that, but it is also compatible with the continuous system as well, actually. So the continuous Darboux system, this one here, is in fact consistent with the discrete Darboux system. So they obey this B, the same B quantities obey differential equations, as well as a set of difference equations of this type. So in some sense, these difference equations form the discrete symmetries of the Darboux-KP system. Okay, so that's all I wanted to say about this. For the time being, we didn't find actually a Lagrange structure for the discrete system, and that is something that is still kind of an open problem. But the statement is that this system of difference equations is multidimensionally consistent and also compatible with the original Darboux system. Okay, so let's make now a connection. Why is it KP? What is it? What has this Darboux system to do with the Kadomtsev-Petriashvili system that comes from water wave theory? And for this, we need to think about actually the Hirota method, the tau, so-called tau function, and the way in which the tau function arises in a kind of discrete version of the Kadomtsev-Petriashvili system. So let me first introduce these functions here, these rhos and sigmas. They are, in some sense, the basic exponential functions in the system, which kind of indicate how, for instance, in soliton solutions, the independent variables appear. So, for instance, these rhos and sigmas would be the key ingredients in the soliton solutions to the KP system. And you see, there are these factors here, which contains the p's. So the p nu is the collection of all these parameters p, q, r, etc. And then we have these n nus. These are these discrete variables over which you do the shift. So when we apply a shift operator like this t here, then basically what we do is to shift this n variable, this n nu variable, by a unit. And then we have here the Miwa variables, these xi's, of which the continuous system depends. And also they are connected with the parameter because they're sitting in this exponential factor together with the parameter. So these p nus indicate the p, q, r, etc. And then these are the xi, the Miwa variables, and here are the corresponding discrete variables. And these rhos and sigmas are the functions, the exponential functions that appear, for instance, in the soliton solutions of this Darboux-KP system. Now, Hirota introduced a very important discrete equation, which is this one, which is a three-dimensional discrete equation, which involves three discrete shifts. And this is sometimes referred to as the Hirota-Miwa equation, although it originally goes back to this paper by Hirota on discrete analog of generalized Toda equation. And this is in some sense the central equation in the whole theory. And in this theory, the p, q, and r play the role of the lattice parameters. So the labels that are used for the Darboux system are actually the lattice parameters, and that's indicated here in these functions by the fact that they are sitting in the factors which are governed by these discrete and continuous variables. So the t operator is a shift not in the PQR themselves, but in the corresponding variables n that are connected with the parameters p. Okay, the Miwa variables are sitting in these factors here, but they can also be seen as arising from a kind of limiting procedure, where you take this operation and then on the tau function. And when you apply this, this is kind of like doing a continuum limit on this Hirota equation, then you get a number of other equations that are also compatible with the original Hirota equations, and they look like this. So here we have a 2 plus 1 dimensional equation, which is two discrete variables, Tp and Tq. So you have two shifts and one continuous variable. So this is a kind of 2 plus 1 discrete version of Kp. And then you have also a 1 plus 2, that means one discrete and two continuous variables. So here we have two continuous variables, and these are these Miwa variables. And this is one discrete because this is actually a shift over a diagonal, and here's the reverse shift over the diagonal. So this, in fact, actually is the two-dimensional Toda equation that was introduced many, many years ago, I think, by Sasha Mikhailov. Now, the Miwa variables, how are they related to the, so the Miwa variables, I call these Xi-P's Miwa variables. They are related to the original time variables in the original Kp hierarchy in the following way, namely that you can think of them as coming from infinite sums with weight of these parameters. So we have these expressions. So these Tj's are the original time variables in the usual Kp continuous Kp hierarchy. And in other words, if you take the derivative with respect to the Miwa variables, then it can be seen as an infinite sum with a kind of weight, which is given by this parameter with respect to the original time variables in the Kp hierarchy. So these Tj's are the ones that occur in the conventional description of the Kp hierarchy, and the Miwa variables are connected via this formula. So in some sense, the Miwa variables form a kind of generating derivatives for the whole set of time derivatives in the Kp hierarchy. Okay, and then what about the B object? What role does it play? Well, there is a particular object that can be obtained by combining two shifts with two parameters. So I've chosen here just generic A and B, but this could be P and Q. And so if you take the inverse shift to A and the forward shift to PB on the tau function, divided by tau, you get a quantity S. And that quantity S is essentially the B variable, the main dependent variable in the Hirota Miwa in the Darboux system, except that you need to actually also to multiply these exponential factors, include them in there. So the original equations in terms of this S take this form, and they can be derived all from the Hirota Miwa equation. But then, in order to make them precisely in the form of the Darboux system, so getting rid of these factors, you need to include these exponential factors. So that is the connection between Kp and this Darboux system. In fact, this S variable itself is of interest in its own right, because you can derive this. Apologies. You can derive a discrete equation for it. So this is for one single S with fixed AB. And this is actually nothing else than the so-called Schwarzian, lattice Schwarzian Kp equation, which is also one of the fundamental equations in the theory of discrete integrable systems. Okay, so this is a connection with Kp. How much time do I have still?
Now it's 1 hour has passed, but no problem. So
Okay.
you can continue.
Well, I don't want to make
for 30 minutes or something. Yeah, no problem.
Yeah. Okay. So I want just to say something about the connection with Chern-Simons theory. Okay, let me skip this. There's also a matrix analog of this whole system. Let's go to Chern-Simons theory. So Chern-Simons theory, of course, a well-known theory which was set up by Chern and Simons in the, I think, late 1960s. And the conventional Chern-Simons theory is usually formulated over as a gauge theory over some Lie group or Lie algebra G, and then you have a connection form, a gauge field, and a corresponding curvature form, which takes this form. And then usually, now there's a subtlety how you define the wedge here, whether you define the wedge as involving a bracket, a Lie bracket, or whether you involve it in an associative product. So in our case, we want to think of this wedge as being just a matrix product of A's and a wedge product in terms of the form structure. So that's important because that kind of convention will influence some of the formulas. So when we write something like A wedge A, what we have in mind is a matrix product between the A's as in the matrix group rather than a Lie bracket. Now the main aspect of the Chern-Simons forms, and here are the form in 3 dimensions and the form in 5 dimensions, and they can be written in any odd dimension, is that if you take the derivative of the Chern-Simons form, you get what's sometimes referred to as the Chern classes. You get the trace of f wedge f. And then the conclusion is that if you think of this as a Lagrangian in an action, then from this one concludes that the corresponding Euler-Lagrange equations amounts to zero curvature condition. And that has been an inspiration for making a connection with integrable systems in a different way. But in our context, actually, this is too strong and also too limited at the same time, because this doesn't indicate any kind of notion of multidimensional consistency. So this is strictly in 3 dimensions, this Chern-Simons 3, and the CS5 is strictly in 5 dimensions. And there's no aspect here of multidimensional consistency yet. You can write down, in principle, also the general form of the Chern-Simons action by this integral, where you involve a kind of dummy parameter lambda, and then you have this trick that gives you all the kind of Chern-Simons actions for any odd dimension, obeying all these kind of properties. And so if you would take the delta of the D of CS, then giving that this is the trace of a wedge product of f's, you will get this, and then you might conclude that if you vary with respect to the variables, then the coefficients f need to be 0. But that is actually too strong for our theory, and actually will, in some sense, kill off the integrability rather than gain it. So what we did is something very curious, in some sense very curious, and makes a connection with our Lagrange 3-form structure for the Darboux system. So we choose now a gauge field, now we call it B instead of A, of this particular form. So here are these B's that we used. I used to have these parameters P and Q, but for simplicity, for notational simplicity, this B is just B, PK, BPL, and these are the P's, or the PQ and R that I used before. So just for notational simplicity, I use now other indices, but they mean the same thing as before. The E's are the generators of an infinite linear group, and they have these properties where the delta is the Kronecker delta symbol. And you take this funny gauge field where you actually have a strange mixture between the form structure, so they attach with these indices here, and the generators of the Lie group. So they are kind of connected to each other in this kind of intricate way. Alternatively, I could have chosen here another gauge field with instead of KL here, that will give us something similar, but it is essentially a similar type of structure. So for just to be specific, we write this gauge field. If we now use this gauge field and we compute the corresponding curvature, we get exactly now the factors are these forms that appear in the Darboux system. So that is very significant, that these are the factors, but we can still have here coincidence of the parameters, and we should, I've not mentioned that, but we should look at situations where the parameters are all different. In any event, so if we now take the Chern-Simons form with this gauge field, so we use this formula, but now applied to this particular gauge field, then what we get is exactly the Lagrange three-form structure for the Darboux-KP system. So this is very surprising that comes out in this very strange way, that we get we get a kind of Chern-Simons. So the Lagrange structure of this Darboux-KP system is essentially a Chern-Simons form, but with this very strange choice of gauge field in an infinite dimensional space. And then if you calculate then the derivative of this three form, then what is important here is that you get a structure here of a double zero structure, but with the essential feature that all the indices must be different. And that comes from the fact that this is combined with this four form here, where actually all the coinciding indices, the terms with coinciding indices, they disappear. And that is what is essentially needed. If we didn't do that, if we wouldn't have that structure where all the indices are different, then we would get too strong a condition, and then that would kill, in some sense, the integrability of the system. So it is essential that this appears in this connection with all the indices different. So the conclusion is that, in fact, this Lagrange three form for KP is a Chern-Simons theory, but a very funny one in a very strange infinite dimensional space. And you can extend that then also to higher forms. So inspired by that identification, you can then look at the higher Chern-Simons action. So here the five form and so on, and you get a similar structure. And now, unlike in the original Chern-Simons theory, where actually the three form lives in 3 dimensions, the 5 form lives in 5 dimensions, and these are totally separate theories. Here the theory is basically one and the same theory, because all these Darboux systems are compatible with each other in multidimensional space. That is the multidimensional consistency. So if you write down the 5 form or the 3 form, they are part of the same theory in some sense. They are not different theories, they are actually connected to each other. And then when you push that idea any further, then you could write, of course, then in any odd dimension a multiform, and then also in principle consider a kind of generating object, a generating action that combines all the forms together for any odd dimension when you integrate over something like a disjoint union of submanifolds of a multidimensional space. So that is the generating Chern-Simons theory. So this is a very strange kind of Chern-Simons theory, which is no longer, I think, a topological field theory like the original Chern-Simons theory, and in some sense incorporates the integrability of the Darboux-KP system. Let me just make a further comment on comparisons with other theories. So there is a development, has been a development in so-called four-dimensional Chern-Simons theory. And that goes back to, I think, originally to Nekrasov in a thesis in 1996 at Princeton University. And then it was taken up or rediscovered by Costello and Witten and Yamazaki and so on, and developed further, where they also tried to explore the idea of a Chern-Simons theory for integrability, but now not for 2+1 dimensional models like in the Darboux-KP system, but for 1+1 dimensional models, so 2-dimensional system. And the way they do that is by incorporating the spectral parameter into the action. So this contains, for instance, this omega, where the omega is some kind of meromorphic one form. And so the space over which you integrate, or the manifold, actually splits up into the space of the real coordinates of your space-time, tau and sigma, and the complex space of the spectral parameter and its conjugate. And then they have a gauge field that they take of this form, which can still be, of course, takes value in Lie algebras as you choose, and it contains only these components because the component with AZ actually vanishes from the action because of this presence of this omega. And what they managed to do then in this way is to derive Euler-Lagrange equations, and the Euler-Lagrange equations contain first this set of equations, which are you can see contains the zero curvature condition, among which, after you do a certain gauge fixing, you get the zero curvature conditions for the Lux pair of an integrable system. So in fact, this gauge connection, the components of this gauge connection up to a gauge transform are the Lux connection of a corresponding Lux pair, and then among the zero curvature conditions, you get the zero curvature condition for the Lux pair, but you also get additional what they call boundary equations, which come from the fact that you have singularities generically in this omega, and they give rise to additional conditions, and these are quite delicate and to deal with, and there are several choices that have been made for this omega, in which case they have been able to derive 1+1 dimensional field theories. So the beautiful thing about this approach is that it gives a kind of natural connection with the classical R matrix structure. On the other hand, it what I think is not clear is that that you have, first of all, this is an action, this is a conventional action, this is not a multiform action, so you cannot, the idea of a hierarchy and all kind of compatible equations is not captured really in this approach. And so you could have here the space-time coordinates sigma and tau, but it's not clear how they extend then to a multidimensional space in which these field theories actually live. So that point is actually not captured by this theory. And another question I have is, since you integrate over the spectral variable, how does that impinge on the solution structure of your equations? Because the integrable equations, they have many solutions. They have soliton solutions, they have finite gap solutions, and quite a variety of solutions. And in these solutions, actually, the spectral parameter is actually constrained to, for instance, a Riemann surface. And how that actually is then incorporated in this theory is also not clear. So that is one comparison. And then there's another thing I wanted to mention is some older work that is, when you look at, again, in 1+1 dimensional field theories, you have a kind of Lux system that can be obtained again with Miwa variables. So these are the same Miwa variables that I mentioned before, but now for a 1+1 dimensional theory where you have this kind of Lux pair, and then that actually links to a kind of general chiral field equation, but the parameter here, this is the same parameter that links to these Miwa variables and is also indeed connected to a discrete system. Then from the Lux equations, you get this system of equations for the coefficients R. So the R doesn't depend on K, but can depend on all the xi's. And then there are two realizations, two way in which you can realize this R so that it solves one or the other of these two equations, namely in terms of a kind of potential function H through this representation, or through another potential function G, which is like a chiral field, in which case you represent the R in this way. In the first case, then you have this set of equations, and that again is a multidimensional consistent set of equations and has a Lagrangian structure of this type, which was already established quite a while ago, in 1988. But it's not clear that there is a multiform structure here, and so far there seems to be a little bit of an obstruction in finding a multiform for this Lagrangian. When you look at this representation, which are the chiral field equations, then you have a natural connection with a Wessel-Witten Novikov action of this type, but with a particular type of coupling constant here, which contains these parameters. And this is significant, this prefactor here, in terms of the topological term. So this action, this Wessel-Witten Novikov action, is well known for this kind of chiral field equation, but this choice of this prefactor is significant for the integrability of the theory, and actually also curiously appears in the work by Costello and Yamazaki from this connection of 4D Chern-Simons theory. So that's one aspect. And then finally, there is a multiform structure that was found in this paper by Vincent Cordelet, Stopato, Vicedo, which actually is a kind of specification of a class of Lagrangians that have multiform structure, which are of the Zakharov-Mikhailov type, and which we investigated in this paper here with Duncan Slay. And that is also a very remarkable structure, because actually the classical R matrix appears in that Lagrangian structure in a kind of manifest way. And that's very beautiful, because when you look at the multiform structure, so in other words, for the closure relation, then that closure relation, you can compute that, holds provided or under the condition that this R, little r here, which is a classical R matrix, obeys the classical Yang-Baxter equation. So classical Yang-Baxter actually then guarantees the multiform or the closure relation. Okay, so that is all I think I wanted to tell. So maybe I'll stop here. So I'll thank you for your attention.
Okay, thank you very much for very clear and interesting talks.
Mm-hmm.